With Professor Marisilva Donadelli, representing and showing the highlights from the Atlas groups in Brazil in the Atlas collaboration. Marisilva is a Paulista in Rio de Janeiro at State University of Rio de Janeiro. Thanks a lot.
Thanks a lot, everyone, for having this opportunity to talk about amazing results, and I hope that I convince you as well that it's great to do physics with Atlas. So I have a disclaimer for this talk because let's say that our group, the Brazilian group at COPE, Federal University of Rio de Janeiro, started contributing in 1988, when Atlas was even not imagined, because at that time, Atlas only was started with the letter of intent report in 1992. But at that time, 1988, the conception was at that time working with a hadronic calorimeter named SPACAL. And SPACAL later turned out to be part of the hadronic calorimeter in Atlas, which is the tile calorimeter. So the COPE group is working with CERN since 1988. And at that time, Atlas was not Atlas, was ASCOT and EAGLE, and the group was interacting with the EAGLE collaboration. So, and here you see in the letter of intent when it all started in 1992. So today we are 5 universities, so we are a cluster. As a cluster, we have Federal University of Bahia, State University of Rio de Janeiro, Federal University of Juiz de Fora in Minas Gerais, Federal University of Rio de Janeiro, and University of São Paulo, and then collaborating 2 other institutes that are not yet officially part of the Atlas collaboration, but are interacting with the cluster. So we have 85 members, 15 researchers considering MNO, and current 23 PhD students. But here I show you, okay, the resolution here is not great, but that's the history of all the PhD students' works that were already defended, and many of them are outside CERN today. They are alumni that had their own industries and in different fields. But anyway, this is a little bit outdated. It's from 2023, but it has a history of the PhD topics defended within the group. So let me talk about this great detector, which is the HL-LHC apparatus. So essentially, we are a multi-purpose detector that is layered surrounding the interaction point. We have a central tracker inside a solenoid. We have the calorimeters and an independent muon spectrometer with a superconducting toroids. And this is the signatures that we trigger for the physics that we explore. And in terms of the main contributions, I'll try to be brief here, but I'm highlighting in terms of physics results, the topics that are just being published with the full run-2 data set. But we also have contributions with the software and computational algorithm development. Many suite of applications which is shared by other LHC experiments and not only Atlas, which is GLANCE. We have dedicated big data processing. So we have a synergy between Atlas and LHC with a tier 2 in São Paulo. We have instrumentation for particle detection and associated systems. And we are also contributing not only with the current Atlas detector that went through a phase 1 upgrade, but also we are involved with the high luminosity LHC phase upgrade. And we are also involved with science outreach activities. So let me just try to highlight a bit of the nice results, and I'm going to highlight the ones that the cluster is involved with. So first of all, let me try to bring you a topic that the cluster is involved since 2013, when Higgs was out of the box. So at that time, we started to investigate the feasibility of the dihiggs measurement with the projection studies for the high luminosity LHC. So at that time, we were using the 2013 ECFA recommendations to prospect how feasible that would be. But why this is so important? Because we have to remember that the Higgs properties is being scrutinized since its discovery by both ATLAS and CMS collaborations. But even though all its interactions, many of its interactions were explored, the self-interaction is still very, very poorly constrained. So the self-interaction comes from the expansion of the Higgs potential around the minimum. So after electroweak symmetry breaking, these are the terms of the potential expansion. In particular, the mass term is well determined here. So this is our current experimental knowledge. But from the second term on, we have no idea what's going on. So it means that we have to probe this by the self-coupling term, which is probed through the Higgs pair production. So with that, what do? Actually, we try to explore as many as possible different final states, trying to keep a compromise between branching ratio and the cleanliness of the final state. So what we have done with run-to results. Okay, so our group is involved with one of these channels, which is the BB tau final state. So this channel is among the three most sensitive channels within the search, together with BB gamma gamma and 4B final state. So our contributions come in 6 papers, both non-resonant, which is the standard model search, and the resonant search, which is depicted here, with the partial and full run-to data sets, plus many projection studies following ECFA recommendations and in CERN-Yellow reports and SNOW mass reports. So our contributions come from editorial boards, definition of analysis strategy, optimization of the final signal discriminant, background decimation, mainly in BB tau, which is really complex final state. So it demands many of person power on this. And here I show you the cross-section, the cross-section limits depicted by the combination of these channels, which is BBLL, multi-lepton 4B, BB gamma gamma, and BB tau, which is the which drives the sensitivity for the expectation value. And here, again, BB tau drives the sensitivity for also the resonance search. So this is not only the only analysis that we are involved with, but we are involved with the standard model working group for precision measurements. And in particular, we were involved with the high MTW measurement, which is a very nice set of measurements because it has the potential of constrain different PDFs. And we were here probing a high region, which was not done before. Another analysis that we are involved with because of the tau final states here is in the exotics group. So here we are probing different resonances from Z prime to leptoquarks. And this is a high mass tau measurement. And our contribution here was more dedicated to M-tau reconstruction studies. And here we placed the limits on the lepton quark masses. Now let me talk about a little bit of instrumentation and figure for the LHC. So the current detector and the past. So We, as a cluster, contributed with the hardware that builds the trigger signal for the tile call in Atlas. We work with signal processing methods for energy reconstruction for the calorimeter towers. We are involved with the first level muon triggers assisted by calorimetry, and use machine learning to extract topologies for the triggering system in the electroweak in the E-gamma group, and also simulation and signal processing developments in high energy calorimetry, and mitigation of crosstalk effects for the liquid argon electromagnetic calorimeter. So here is a picture that depicts the contribution, direct contribution from a copy, Federal University of Rio de Janeiro and the Federal University of Juiz de Fora. And moving on, so here for the liquid argon calorimeter, the contribution was mainly developed for the phase 1 system, which is the current upgraded liquid argon for the run tree. So we, in this is preliminary study at the very beginning of the phase 1 upgrade, when we were in shutdown, preparing for run 3, we performed radiation testing of the main components of the prototype type phase. And so especially this was really important for the reading supercells, which is the new configuration of for the triggering system of the liquid argon. So in this particular point of view, some of our PhD students worked on baseline corrections for the firmware in this new sum up of cells for the upgraded trigger system. So this was very important for run 3, where we have this level of pile-up, and the code developed since then is being used by the subsystem. In the tile calorimeter side, we have a dedicated tile call assisted muon trigger. This electronic module is the main component responsible for merging the muon information from tile call with the thin gap changer sector logic for the trigger. It was developed at the end of run 1, and it's still in operation until today. In terms of the trigger system, the main development is the neural ringer, which is a method for online electron identification. Today, the ringer algorithm uses this as input energy sums of 50 cells, 50 concentric rings, not anymore 100 here, because we are also dealing with the boosted electrons. So the system is the standard electron triggering algorithm since 2017. In terms, okay, so this is the trigger results now with the neural ringer being set up for the Atlas trigger, high-level trigger system. So I'm going to skip this. Let me talk a bit about the computing. So we have the GLANCE project. The GLANCE is really something that also makes us proud, because it's an essential software management tool that has the main objective as maintaining automated web-based solutions. So you can see here that it's commonly shared not only by us in Atlas, but ALICE, LHCb, and the future inner tracker for the high luminosity LHC phase in Atlas. So here is, we have just a table that summarizes all the systems and users and the number of requests per week. We also have a tier 2 that is shared between us and ALICE in the same cluster in the High Energy Physics Instrumentation Center hosted by University of São Paulo, which is in operation since 2022. And let me talk about our bright future ahead of us. I mean, not so ahead of us, because we are facing now the high luminosity LHC. And as you can see here, today, this is our configuration in terms of number of protons per bunch. We have today a level of 1.6 times 10 to 11 protons per bunch. And then we are going to almost double it in the high luminosity LHC phase. But then looking at the integrated luminosity per year, comparing with what we had as the LHC design, which is 30 inverse femtobarns per year, here we have 1 order of magnitude more. So we have to prepare ourselves for the challenge. So Atlas is going to be completely refurbished in terms of the inner tracker detector. We are going to have new and upgraded luminosity and forward detectors, new muon chambers and electronics. We are going to have electronics upgrade for the calorimetric system, an all new silicon inner tracker, and a new high granularity detector, which is very important for our cluster. So you know that most of the LHC data is expected to come in this phase. So now we have only 5% of the expected data of the LHC. So we are going to have an unprecedented 200 simultaneous proton-proton collisions at every 25 nanoseconds. So pile-up will dominate the environment. So it's a very challenging environment to complete track vertex association during event reconstruction. And mainly in the forward region where we lose resolution because the tracking cannot cope with this, we need to add another dimension in terms of information to completely characterize the event. So the HTD comes at a hand with Brazilian contribution to the sensors being around $172,000 in construction and commissioning. So the HTD facility at USP is hosted at the High Energy Physics Instrumentation Center. USP and CERN are the two main institutions that are evaluating the performance of the sensors that are produced by HTD, as Marcelo already mentioned it, and it's going to be shared by Alice as well. So we have already measured 100 test structures from 24 pre-production wafers for the HTD, and this is the sensors evaluating room especially dedicated for this task. We are also working with the 4D tracking pile-up mitigation. This is a PhD student. Okay, I'm finalizing, sorry for this, which is a PhD student totally dedicated to use graph-based neural network approach to integrate the new silicon tracker and the HDD information. And I'm going to skip this, I'm sorry. And in terms of outreach, we have virtual visits and more than 6,000 participants that integrated the virtual visits organized by the cluster since 2012, and always working also with outreach in terms of master classes, hands-on particle physics. USP is involved since 2015, whereas since 2018. And my final remarks, Brazil has contributed to Atlas since its conception. Our cluster is involved with all the data-taking periods, mainly in physics analysis, instrumentation, trigger and calorimetry, computing, and outreach. In the phase 2 projects, we are involved with the HTD, with a dedicated facility for evaluating the performance of sensors, working with pile-up mitigation studies with graph neural networks and the new framework. We're also involved with a level 0 global E-gamma trigger for this phase and new energy reconstruction methods for calorimetry. And I'm so sorry, thanks for your attention.
Thanks so much, Marisilva. It's a lot of work.